All right. Well, it's truly a very special pleasure for me to be able to introduce Jared. Jared Novick is an associate professor in the Department of Hearing and Speech Sciences at the University of Maryland. A little bit of his bio: his PhD is in cognitive neuroscience from the University of Pennsylvania, where he trained with John Truswell and Sharon Thompson-Schill. And he completed a postdoc in brain and cognitive sciences at MIT, after which he joined the Center for Advanced Study of Language, affiliated with the University of Maryland, before joining the Department of Hearing and Speech Sciences. Jared's work is highly interdisciplinary, investigating the interplay between neural and cognitive mechanisms affecting sentence processing, memory, and cognitive control. Even during his graduate career, the seeds of this work can be found, where he, with his co-advisors, published papers proposing that cognitive control, a domain general cognitive process, is involved in repairing garden paths, which will be linked to some of the work that we will hear today. He's published very widely in multiple articles appearing in high-impact journals such as Brain and Language, Cognition, Journal of Experimental Psychology, Learning, Memory, and Cognition, and Psychological Science, just to name a few. And just very recently, together with Al Kim, he's the recipient of an NSF grant titled Direct Impacts of Executive Functions on Language Comprehension: Evidence from Eye Movements and Electrophysiology. I've had the immense pleasure of working closely with Jared, so I'm going to share a personal memory that I don't think I've ever reflected on with Jared before. So in 2008, I attended the AMLAP conference in Barcelona, Spain. That was my third year as a graduate student, my second conference ever, and my first international conference, and I was totally alone. His graduate advisor, John Truswell, from whom I had taken a class at an LSA Linguistics Summer Institute, and who later became my own postdoc advisor, introduced me to Jared, and he quite literally became the friendly face to me at the conference. He was the person with whom I could share a meal, talk about research ideas, even from my very naive and green perspective. And he truly showed me the humanity behind research, networking, and conferences. And I'm thankful that over the years, we've gotten to collaborate and work together, and that I've gotten to know him better. I genuinely look forward to our interactions and our meetings, especially because I know that I will continue to learn from him at every single one of them. So today, I'm hoping he will share that with all of you, as he has shared that with me. And he'll be giving a talk titled Direct Impact of Cognitive Control in Sentence Processing and Comprehension: The Importance of Cognitive States versus Traits. So please let us all give him a warm round of applause.
Well, thank you, Jorge, so much for that really lovely introduction. And the feelings are entirely mutual, and I appreciate reflecting on that reflection from MLAP. I remember that time well. That was very generous, so thank you for that. And thank you, everyone, for having me here. I've been looking forward to this exchange for a while, and I can tell already that it's a fun group. And so I don't know what your ground rules are for questions, but I can be pretty flexible in how this goes. Maybe, for starters, we can just think about saving questions until the end. I'm going to be sticking around for a while, unless there are needs for earnest questions or clarification questions. Feel free to just interrupt me. So what I want to do is talk to you a little bit about some old stuff and some new stuff from my lab that will attempt to weave together a narrative about how non-linguistic cognitive systems contribute to real-time language processing. And as we started to talk about at the beginning of this session, the usual typical approach to this kind of issue is to talk about group comparisons or trait individual differences, right? People with ability X also have ability Y. And when we find those associations, we infer that those associations are meaningful, and they are, right? We infer something about the tasks that we're studying share common mechanisms, and I'm going to do some of that today. But I'm also going to talk about some of the limitations to that approach and shift to tell you that comparing people with themselves rather than to each other under different states of cognitive engagement from moment to moment can also tell us a lot about the architecture of the language processing system and what role these mechanisms play in real time. I don't have a lot of time. Jorge really put the shackles on me and said, talk for 35 minutes. No, I'm just kidding. We've probably done about 24 studies or so in this area. I'm going to tell you about 3 maybe-ish. But again, I'm staying late so we can talk more at the end, and feel free to ask all kinds of questions. Oh wait, that doesn't advance. So I want to start with a story to begin this. It goes back to my graduate school days in Philadelphia when it was a hot summer afternoon, and I was online at our beloved food truck outside the Institute for Research in Cognitive Science. And I got online and I asked the vendor if I could please have a lemonade, but without any ice. And she said, sure, buddy, no problem, I got you. And I saw her take the cup of ice and she automatically dipped it into the bin of ice and filled it up with lemonade, which is exactly what I didn't ask for, right? And we kind of looked at each other and she recognized immediately that she had made a mistake. And she said, sorry, man, let me just get you another one. And she took the cup and she dipped it into the bin of ice and she filled it up with lemonade. And immediately realizing her mistake, I'm now questioning what's happening here. She says, I'm going to get you a third time's a charm. And she took the cup, she dipped it into the bin of ice and she filled it up with lemonade. And the point of the story that I'm trying to tell you is that as we go about our day, navigating and perceiving the world around us, we sometimes encounter moments when we have to rein in the first cognitive reaction that comes to mind in view of new rules or goals or plans of action or instructions. And this requires cognitive control, which is our ability to adjust thoughts and actions when we're confronted with conflicting information in the environment. And in my lemonade example just now, my instruction just competed with the vendor's habitual routinized way of completing her task of making lemonade, especially, on a hot summer day in Philadelphia. Nobody's asking for lemonade without any ice. And there are, of course, many real world tasks that require the deployment of cognitive control procedures. And as you all know, and as we've been talking about already, in the laboratory, the canonical cognitive control task is the Stroop task, in which the task goal, the instruction is to indicate the ink color or the font color, which conflicts with a prepotent bias to read the word. And here, cognitive control is needed to rein in that knee-jerk reading response and instead promote the color naming one instead. And for years, I have been beating this drum with my colleagues and students that in the domain of language processing, one important cognitive control function is to revise misinterpretations of language input. And here is why and how. I'm going to try to flesh this out for you. Readers and listeners commit to sentence interpretations as we encounter language input incrementally, right, as it is perceived. And that is to say, people don't delay interpretation until a sentence or even a single word has unfolded entirely, right? We generate provisional analyses moment by moment, rapidly consulting multiple sources of evidence from both linguistic signals, syntactic cues, semantic cues, and also the contextual environment to guide our comprehension procedures moment to moment. But sometimes what happens is that listeners' initial interpretations of sentence meaning sometimes turn out to be wrong when various evidential cues that arrive late in an utterance conflict with earlier cues, which forces the need to revise. And you kind of have to slam on the brakes and go back and recover an alternative interpretation of sentence meaning. Despite years of research into the processing stages involved in language comprehension, actually very little is known about how we regulate our interpretations to prevent failures in comprehension and in communication more broadly. So we have been asking questions about whether cognitive control enables revision, sort of like a Stroop task in the syntactic domain, where we have to override reliable but currently irrelevant interpretations of the input. And I'll use a well-known example just to illustrate when listeners have to resolve conflict to override a default interpretation during real-time processing. This is just one example. I'll use it throughout the talk today, just for ease of storytelling, but it isn't meant to be exhaustive of the kinds of language comprehension situations that give rise to conflict and the need for cognitive control. So consider following this instruction as it unfolds incrementally, right? Put the apple. And you have a verb, right? And you know that a speaker has to have a goal in mind when you hear the verb put, right? Verbs don't lie to you. This one arrives early. It predicts structure. You can't tell someone to put something without telling them where to put it. The next increment unfolds on the napkin, and readers and listeners commit rapidly to the goal or destination interpretation of that prepositional phrase. But late arriving evidence, as the sentence continues to unfold onto the box, suggests that the box is the actual goal, which conflicts with listeners' early preference to analyze that first prepositional phrase on the napkin as the goal. And they realize now that the box is the goal, and they have to override that first prepositional phrase and characterize it as a modifier phrase, which provides more information about the apple, namely that it's currently sitting on a napkin, right? To allow the box to be the ultimate goal. Yeah, everybody good with me so far? Okay, so eye gaze studies, and there are several of these, have shown that while following this kind of instruction, right, containing the verb put with a very strong bias that arrives early, like put the frog on the napkin onto the box in the presence of toys here instead of apples. When listeners hear put the frog, that first increment, their eyes rapidly converge on the target here, the frog, right? There's only one frog in the scene. When they hear on the napkin, they quickly look over to this incorrect goal, right? This incorrect goal here, this empty napkin, even though this frog is already sitting on a napkin, right? Suggesting that they're considering the goal analysis of that first prepositional phrase rather than as a modifier. Upon hearing that conflicting, disambiguating evidence onto the box, healthy listeners will look back at the frog that's sitting on the napkin, realizing that the phrase is a modifier, and they quickly revise, looking toward the correct goal, the box in the scene, as an indication that they've revised. So, and those eye movements will guide their hand actions, and adults will pick up the frog and then put it on the box as instructed. Okay. Now, of course, adult listeners can adjust their interpretations in real time, rarely failing to understand what a speaker says. But the ease with which we revise betrays the intricate role that conflict detection and cognitive control procedures might play to prevent comprehension from running aground moment to moment. So one way to address the question of whether cognitive control is involved in revision procedures is to ask whether populations with poor cognitive control fail to revise. And one piece of tantalizing evidence that supports this idea is that 5-year-old children on the put task show a very different pattern of eye movements and actions as healthy adults. So young children will incrementally interpret just like adults. They commit to the incorrect goal upon hearing on the napkin. But they also fail to revise. They pick up that frog and they'll put it on the empty napkin, involving this incorrect goal in their actions, in their act out performance, 60% of the time, something that healthy adults just don't do. Right? And some people, including me, have ascribed this pattern to the late maturation of frontal lobe systems that are important for cognitive control, that coincides with the protracted development of cognitive control abilities in young children. We were talking about our kids before the start of this talk. If you've ever met a 5-year-old, you know that he or she can't not do the first thing that comes to mind. If you don't believe me, I invite you to my house. Okay. But kids differ than healthy adults in lots of ways, including in their experience with language. So I want to put a little asterisk next to that kiddie finding, and we can come back to that later. But what other evidence do we have, maybe more direct evidence, that cognitive control is related to language processing in this way? And there are several neuroimaging studies. If you look at many, many papers that have tested healthy adults across many different conflict resolution tasks, including Stroop, including flanker variants, including syntactic ambiguity resolution, what you'll note across a range of dozens of studies now is that this little purple patch of cortex in the ventrolateral region of PFC, which I've shaded purple here, a region of the brain called the left inferior frontal gyrus, is consistently recruited under conditions of having to resolve conflict, despite differences in task stimuli and task properties. What we also know is that patients that have circumscribed damage to this region, can you see my cursor here? I don't see it. That doesn't matter. Patients that have circumscribed damage to the LIFG have deficits in cognitive control. They will routinely demonstrate exaggerated effects in both reaction time and error rates on Stroop and Stroop-like tasks. So we have tested a patient with focal damage to the LIFG on the put task, and we'll call the patient IG, very clever, right, for inferior gyrus, and he shows the standard cognitive control deficit, right, exaggerated performance on the Stroop task. And what we ask here is whether that cognitive control impairment results in a failure to revise, kind of like what we saw with young children a moment ago. And we compare that patient to two control patients and a number of healthy age and education matched adults. Patient 1 and patient 2 both had fairly widespread damage to the left hemisphere, but crucially, their damage did not include the LIFG, right? That's what I've circled red here. And they had their conflict resolution abilities intact. In other words, they showed Stroop-like performance within the normal range. So what do we see? On the put task, we'll look at P1 and P2 first. They look just like healthy adults, right? They incrementally interpret language just like you and me. When they hear on the napkin, they'll commit to that goal analysis, right? They'll look over at that incorrect goal. But they promptly revise upon hearing onto the box, just like healthy adults. And those eye movements guide their hand actions, and they pick up the frog and they'll accurately put it on the box. Patient IG, by some contrast, he also temporarily misinterprets. He commits to that goal analysis of on the napkin. And as the sentence unfolds and he hears onto the box, he fails to revise. He continues to look at the incorrect goal. He picks up the frog and he places it on the empty napkin as if he's not arriving at the modifier interpretation. He's sort of gunning for that goal interpretation. And just like a 5-year-old child, he does not recover from the misinterpretation. So he fails to override that initial processing commitment. Crucially, when you make the sentence unambiguous, you include this complementizer that's, which now forces the modifier interpretation of on the napkin. Patient IG does just fine. He picks up the frog, he puts it on the box, suggesting that his difficulty is rooted in the conflict, right, the ambiguity of the sentence, rather than in long, complex sentences or a lack of grammatical knowledge per se. So to summarize what we've got so far, we see in LIFG patients a co-impairment in cognitive control and sentence revision abilities, a similar kind of correlation in 5-year-old children. Their delayed cognitive control abilities correlate with their delayed sentence revision abilities. We see co-localized brain activity in healthy adults in the LIFG, right, for a range of conflict resolution tasks, including Stroop, including flanker, including memory tasks that manipulate the demands for resolving interference, and also in sentence revision. I haven't told you about, in 2 studies that included multi-week training on a Stroop-like task led to post-test improvements on the train tasks, but also in sentence revision abilities, indexed by both online eye tracking and offline, namely comprehension accuracy measures. Those studies were conducted by my former student, Erica Hussey, who has moved on to continue to do wonderful things. So together, what these data suggest is a role for cognitive control in language processing. The data so far indicate some shared processing demand, and that there is some stable, perhaps cognitive control ability or trait that is common across language and non-language tasks, at least in special groups, right? Patients, kids, trainees. So if you have good cognitive control, then you have a greater ability to recover from temporary misinterpretation, because that too is a cognitive control task. But the population differences we show in patients, because they are correlational, right? There's a co-impairment, and in adults, it's just co-localized recruitment of the LIFG. Of course, cannot establish that it is poor cognitive control that impedes successful revision in a causal way. The data also, on the flip side, those patterns can't tell us that it is cognitive control engagement by healthy adults that is what is assisting them to revise following their early misinterpretations of language input. And I would say that even the training results that I very briefly described don't demonstrate that it is cognitive control procedures that kick in at post-test at the moment that it is required. Moreover, what I want to say is that traditional individual differences comparisons sometimes ignore the fact that the relative engagement status of cognitive control fluctuates throughout the day, and even throughout a short-term activity like listening to a talk or like making lemonade, right? Missing important information about how variation within individual states of engagement contribute to interpretation procedures. So we wouldn't want to characterize everyone who has a lapse necessarily in the low cognitive control bin, right? So it suggests to a certain extent that some individual differences approaches may not confidently be measuring cognitive control abilities that are necessarily fixed or stable when we measure these traits in the lab without paying attention to what state an individual might be in. So the cognitive control and language processing account makes the critical prediction that there is a causal interplay between dynamic engagement of cognitive control and effective recovery from misanalysis. But the correlational nature of the evidence so far leaves open key questions about whether there is this cause and effect connection. And addressing this kind of issue requires a paradigm that manipulates cognitive control and examines its effect on sentence processing. And this is where we begin to diverge from prior research, including from my own prior research, because this is what's going to help us determine whether people's revision abilities get pushed around depending on their state, the relative state of cognitive control. We're going to use a standard laboratory cognitive control task to manipulate the states of cognitive engagement in real time in the context of a well-studied phenomenon of human cognition, where the initial detection of conflict, right, like on the Stroop task, the word brown and blue font, triggers cognitive control engagement. By contrast, brown and brown ink on the right does not. And such cognitive control engagement facilitates performance on subsequent trials that also require cognitive control. So on the left, you have faster response times and greater accuracy to saying green to the word red in green font, compared to when cognitive control had not been previously engaged here on the right. And this effect is known as conflict adaptation. Good? Good. Okay. So our first foray into this area was to test whether people's discovery of a misinterpretation actually regulates the state of cognitive control engagement. This is my former student, Susan Tubner-Rhodes, who's now at Auburn University. She was the driving force behind a collaboration with me and Irene Kahn. And she asked, is sentence revision even a cognitive control task in the first place? Is it subject to the same conflict adaptation phenomena as canonical cognitive control tasks like Stroop? So we designed a study that tested whether reading temporarily ambiguous sentences that were ripe for misinterpretation, like this one on the left, the man accepted the prize would not go to him, where the verb accepted is strongly biased to take a direct object, and the prize is a perfectly good direct object for accepting, but it turns out that it is, the prize is the subject of an embedded sentence complement, right? Compared to on the right, where we just include that complementizer that, right, forcing the sentence complement interpretation of the sentence. And we're asking now whether this kind of manipulation impacts performance on an ensuing incongruent Stroop trial, right? Specifically, does the need to revise on one trial engage cognitive control, thereby resulting in better performance on the canonical cognitive control task, here, Stroop? Namely shorter response times and higher accuracy rates. If so, then this would tell us that recovering from misanalysis during real-time language processing deploys cognitive control mechanisms on a pretty short time scale. Of course, we rounded out the design. We have both sentence types also appeared before congruent Stroop trials. Here, there should be no effect. So we're looking for a previous by current trial type interaction. Right, we expect a regular old Stroop effect after unambiguous items, maybe a smaller Stroop effect after ambiguous sentences. We have lots of filler items, lots of filler sentences, lots of other Stroop type items that are not conflict or incongruent, right? Regular words in colored fonts. We pseudo randomly interleave the trial types so that a participant can't predict what kind of task or trial is about to come next. Okay, so first I should say that we find the usual ambiguity effect, right? In the disambiguating region, people were reading the sentences in a moving window paradigm. So in that would not region, we see longer reading times for ambiguous over unambiguous, all right? They experience the typical conflict, and we see a regular Stroop effect, right? Incongruent performance is worse than congruent performance. The question here is whether that is modulated by the prior sentence type. And the easiest way to show you the data is like this, right? So I'm plotting the Stroop effect here for response times in milliseconds. It's just incongruent minus congruent, right? Following ambiguous sentences versus following unambiguous sentences. Higher on this scale means less control, lower means more control, right? And what we see, there is a current by previous trial type interaction. All the action is in the following the ambiguous sentences. But you see that people take reliably longer to respond, right? There's a larger Stroop effect following unambiguous sentences as compared to ambiguous sentences. And we see a similar kind of effect for error rates, where now there's basically an elimination of the Stroop effect in error rates following ambiguous sentences as compared to unambiguous sentences, where both in response time and error rates, the Stroop effect is preserved when cognitive control is relatively downregulated, right, after unambiguous sentences. So that performance on the Stroop task, our canonical cognitive control measure, was shaped by the prior sentence type, suggests some sort of cause and effect relationship, right? Temporary misinterpretation of language input engages conflict resolution procedures that regulate behavior, influencing performance on an ensuing cognitive control task, telling us that revising misinterpretations of language input is subject to the same kind of conflict adaptation phenomena as traditional measures. So it tells us also that the language context, having to revise versus not, engages cognitive control procedures. And particularly that language can regulate states of cognitive control engagement on a moment-by-moment basis. Okay. But those findings don't say anything about whether cognitive control engagement assists sentence revision, right? That's not our outcome measure. Stroop is our outcome measure. So we want to know if the revision process itself is impacted by the relative engagement status of the cognitive control system. In other words, when we vary the state of cognitive control moment to moment, what are the effects of this subtle manipulation on interpretation and reinterpretation procedures? Do even healthy adults sometimes look like LIFG patients with cognitive control deficits, right? Do they sometimes fail to revise when cognitive control is off, right? For lack of a better term. This is not a question that we can ask using typical individual differences or average group comparison approaches. So to address this question, I'm going to tell you about some work that was spearheaded by my wonderful former postdoc, Nina Shu, who's now at the NIH. And some of these studies were also in collaboration with Stephanie Kaczynski at Walter Reed. So what we did is manipulate relative cognitive control engagement with Stroop conflict and no conflict trials, which preceded spoken instructions that contain the ambiguous put materials, right? Put the frog on the napkin onto the box while we're measuring listeners' eye movements. And we also had unambiguous trials to test the specificity of any effects on syntactic revision processes, right? Put the frog that's on the napkin onto the box. We're removing the conflict by forcing the modifier analysis. So when cognitive control is engaged, do adults have an easier time revising reflected in more correct goal looks? Remember, healthy adults temporarily misinterpret. They look to the incorrect goal before the correct goal, hence looks to the correct goal as our measure of revision. Okay. So let's pretend first. And what do we expect? If cognitive control engagement modulates consideration of the correct goal, what do we think we're going to see? So I'm plotting here on the y-axis the proportion of fixations on the correct goal, right, the box, as an example, as a function of sentence region on the x-axis. Right, I'm going to plot ambiguous conditions in blue and unambiguous conditions in red. So first, what you would expect to see is that the onset of onto the box, when listeners get conflicting evidence about the correct goal and ambiguous conditions, we expect listeners to look more to the box in unambiguous sentences versus ambiguous sentences, which reflects the delay recovering from the misinterpretation, right? They're looking at the incorrect goal first and the empty napkin first before they get to the box, right? So that's just the regular standard ambiguity effect. But how is that pattern modulated by the prior Stroop trial type, which manipulates the relative engagement status of cognitive control? I will show you prior Stroop incongruent trials in dashed lines and congruent ones in solid lines. And if cognitive control engagement facilitates recovery from misinterpretation, then in ambiguous conditions, listeners should look more to the correct goal following Stroop conflict, right? That's the blue dotted line, than those following congruent trials, the blue solid line, when there's no cognitive control engagement. This would suggest greater revision when cognitive control is relatively upregulated. And there should be no effect of the Stroop manipulation on unambiguous sentences, those red lines, because there's no conflict in those sentences, thus no need for cognitive control. But alternatively, if cognitive control states, right, that manipulation of state within an individual moment to moment does not impact revision, then we'd expect just a main effect of ambiguity with no impact of previous trial type, right? In other words, we'd expect no conflict adaptation. Okay, here are the actual eye movement data, the real deal. So we see that across the 4 conditions, there are no differences that emerge prior to the point of conflict, right? That totally makes sense. They're not looking much at the correct goal anyhow, because it has not even been uttered, right? We first see that ambiguity effect begin to emerge as listeners hear onto the, right? That is, as new input conflicts with the initial analysis, which also makes sense, right? There are fewer looks to the correct goal in ambiguous versus unambiguous sentences. And critically, upon hearing box, right, specification of the correct goal word, listeners look more to the correct goal in ambiguous sentences preceded by incongruent trials, Stroop trials, when cognitive control is engaged. That is, they look away sooner, and we have, that's a different dependent measure, but we have that too. They look away sooner from the incorrect goal compared to ambiguous cases when cognitive control is not engaged. As expected, cognitive control here does not affect looking patterns in unambiguous sentences when it's unnecessary to control our interpretations. And these eye movement data so far, and I'm not even presenting you any timing information here. I can show you that slide at the very end, but the eye movement data are consistent with the notion that cognitive control engagement impacts revision in real time, increasing revision procedures, and other data suggest that they are doing so earlier in time. But does it actually prevent misinterpretation? Does cognitive control engagement result in fewer instances of incorrectly putting frogs on napkins instead of boxes? And I told you at the beginning, young kids who have protracted maturation of cognitive control, they do that. Patients with cognitive control deficits, they do that. But healthy adults, they don't really do that. Right? Another way to ask this question is, well, even adults sometimes do make some errors in comprehension. Do they make more of those errors and fail to fix them, sort of like LIFG patients, when the state of cognitive control is relatively downregulated? So here I'm showing you the proportion of incorrect actions, right? Those that involve the incorrect goal, right? Putting the frog onto the incorrect goal here, to show you how often the incorrect goal was involved. One of my 3 children is trying to bust in here. So never knew that Zoom had a virtual background that looks like real children, right? They might come in, they might not, I don't know. All right, so the first thing to note here is that even healthy adults do actually sometimes make errors involving the incorrect goal under ambiguous conditions, right? About 13% of the time, much lower than the 60 or 70% that patients show. Now let's look at those error patterns as a function of cognitive control engagement. Now we see that when the state of cognitive control is on, again, I'm just using a shorthand here, following Stroop conflict, right, that blue striped line, cognitive control by and large prevents erroneous interpretations. So there's only 7% errors. Okay? But when cognitive control is non-engaged in the moment on this trial by trial basis, healthy adults make errors about 20% of the time, nearly 3 times as much. So in other words, when cognitive control is relatively less engaged in the moment, healthy adults behave more like LIFG patients, right? The engagement status of the cognitive control system can reveal the causal impact of this system on interpretation procedures and sometimes show us that a person with trait X, right, healthy adult, generally good cognitive control, can sometimes look like a person with trait Y, a different group entirely, right? And it can tell us why they do so by looking at these manipulations of their state of engagement in the moment. Individual differences methods, and we've tried this ourselves, which are correlational in nature, don't allow such inferences. So, all right, one possibility here is that the Stroop task is a verbal task, and maybe it engages a cognitive control system that operates over only verbal linguistic material, which would suggest an element of domain specificity to that account, right? If we're interested, let's see how to put this. If we're interested in how the moment-to-moment status of cognitive control engagement affects communication, then we also want to know what sorts of activities generate fluctuations in cognitive control and how they impact comprehension, namely how general are the cognitive control procedures. So in follow-up work, we aim to replicate the previous findings by replacing the Stroop task with a nonverbal flanker task, where now people have to indicate the direction of a central facing arrow despite surrounding arrows that point either in a congruent condition or an incongruent condition, creating conflict and the need for cognitive control in the conflict condition. Sorry, I'm doing something naughty here, which is I'm showing you the proportion of correct actions, which is the opposite of what I showed you before, which was incorrect actions, but it's more or less the same deal. What do we see? When cognitive control is on, we again see better revision here over on the right. There's about, this is correct actions, right? When people go directly from the frog and they put it on the box. But if you want to think about it in terms of errors, there's about 5% errors involving the incorrect goal when cognitive control is on and 16% errors when cognitive control is off, right? Replicating the Stroop patterns that I just showed you before. Similarly, nearly 3 times as many errors when cognitive control is relatively downregulated. In the interest of time, I don't even know what time it is. How are we doing here? I'm not showing you any eye movement patterns here in the interest of time, but they also replicate. There are more looks to the correct goal after incongruent flankers. It's nearly the identical pattern. So inferences so far. The data from the previous couple of studies that I was showing you suggests that the conflict control mechanisms that support sentence revision are domain general. Namely, they function systematically over a variety of linguistic and non-linguistic representations alike, and are subject to similar state-based effects. I hope the question that you are all asking yourselves now is it really cognitive control? Like, how do you know this is really about these conflict resolution mechanisms? Could these effects just simply be ascribed to other cognitive systems that engage under harder task conditions, like just prolonged attention across trials, right? For instance, Stroop and flanker are not pure measures of cognitive control. They're challenging. They result in multiple types of cognitive engagement beyond conflict detection. and ensuing adjustments in cognitive control. So it remains possible that listeners' revision procedures were enhanced just by the more effortful attention demands that are imposed by tricky Stroop or flanker items, rather than regulated behavior that's triggered by conflicting representations per se. So next, we test whether harder versions of a sentence processing task, due to temporarily competing interpretations, right, on the put task, are eased not just because listeners increasingly engage when confronted with tasks requiring greater effort, but more specifically because cognitive control has been recruited to handle competitive interactions. So here it's basically the same setup as the flanker, but instead of manipulating conflict, we're just manipulating attention. So here what people have to do in the less attention trials is just indicate the direction that all the arrows are facing. And in the more attention, over something, I think it's 90 seconds, we'll have arrows all pointing in one direction, and then they'll suddenly flip, right? They're all pointing in the same direction at unpredictable intervals, and for different durations over the course of a 90-second trial. So from trial to trial, subjects never knew if they were getting a less attention or a more attention condition. If they were getting a more attention condition, it could flip anywhere between 1 and 4 times at totally different timing intervals. So in order, they had to stay on task, maintain their attention, hit a button every time the arrow flipped. The more attention trials are harder, but they don't involve conflicting representations. They make more errors, but people actually notably stay on task, right? And they're hitting the button. There's a measurement of response time that is tied to their final button press, and those response times are not any different than in the less attention condition. So while it's harder, they make more errors, they're maintaining their prolonged attention throughout a trial. Yet, people's state of prolonged attention across effortful trials does not modulate their ability to revise on the put task. So I don't have a figure here. I could show you one at the end, but they're about 91 to 93% accurate regardless of the attention manipulation. So what this seems to indicate is that our effects, the previous effects that I was describing, seem to be due to the detection of conflicting representations, right? Stroop, flanker, syntactic ambiguity resolution, and the engagement of cognitive control. It's not simply about paying attention or just more effortful processing per se. We have 2 other studies that also subtly manipulate cognitive control versus attention, and find the reappearance of the carryover effect when conflict control processes are reintroduced or engaged. And again, the disappearance of the effect when attention, but not cognitive control, is manipulated. So I think these effects come and go depending on what systems states we vary, right? Attention versus cognitive control, because while they're related, there are separate constituents of executive function and may impact language comprehension in distinct ways. At least 2 distinct ways. So I will define for you what I mean by attention control, which is that it regulates the collection of exogenous information from the environment by selectively biasing perceptual processing toward a single channel. And it's what I mean by this is typically what we colloquially mean by paying attention, really, right? In general, attention control supports humans' ability to orient to sensory input, and gather information from the signal across prolonged periods of time. And in the domain of language processing, for instance, one important attention control function might just help listeners extract the intended signal by guiding perceptual processing to favor one talker's voice over other sources of noise. Whereas cognitive control acts on endogenous, not exogenous representations, right? Endogenous representations. Cognitive control regulates thoughts and actions when the intended characterization of the input conflicts with a more dominant one. For example, cognitive control helps revise an interpretation of a sentence after a listener discovers a misanalysis, and they have to re-rank interpretations and recharacterize how they interpret the language input by biasing internal representations toward relevant over prepotent but currently irrelevant ones. I really want to stress this point. Understanding the distinctive contributions of cognitive control and attention control is really important because emerging findings indicate that these two sorts of executive functions influence different aspects of language comprehension. They have different time courses, right? Cognitive control might be more transient and attention control is a bit more sustained. They are served by distinct neural mechanisms in EEG signals and theories of language comprehension that fail to account for these kinds of contrasts. And most theories don't, right? We all see people using terms like executive function, attention control, cognitive control interchangeably in the literature. I think this is a problem because what it would do is lead to mixed empirical results and conceptual mistakes. And this is the focus of some new research that I'm doing in collaboration with Al Kim at Colorado. So, cognitive control, I've defined for you as our ability to regulate mental activity to resolve among competing characterization of some stimulus. And during language comprehension, one important cognitive control function may be to help revise misinterpretations once new evidence signals a quite different interpretation than the one a listener has committed to help bias processing toward relevant over irrelevant cues to interpretation. One piece of evidence is that patients with cognitive control deficits fail to revise, which impedes communication. But we have asked whether healthy adults' revision abilities differ depending on their state of cognitive control engagement and whether there is a causal basis for this relationship. And when manipulating cognitive control using Stroop task, a flanker task, we see fluctuations in cognitive control activity that modulate comprehension success, suggesting a cause and effect interplay that can be pushed around within healthy individuals. Do you remember at the beginning, I just want to give a very quick plug to my excellent student, Zoe Ovens. Remember earlier I told you that young children often fail to revise and that their failure has been ascribed to the protracted maturation of cognitive control abilities, namely to their trait performance. Well, Zoe's been testing this idea directly using the very same methods that I've been describing that manipulate cognitive control engagement. And she would tell you, wrong. Well, it's not wrong, it's just nuanced, right? She would tell you that kids' failure to revise in the put task increases when cognitive control is engaged, which is the opposite pattern of adults. And she says that this may be because verbs like put reliably predict sentence structure. So children may rely on verbs, right? Verbs don't lie to us. So they increase their reliance on verb, on the napkin, goal, right? And cognitive control just increases their reliance on verbs at the expense of subsequent evidence, while adults' cognitive control helps them focus on revision cues, right? Which is not what you would expect from the correlational trait data, right? Kids' cognitive control performance correlates with their ability to revise. More equals more in those correlational studies, right? And less equals less. Now, when Zoe changes the sentences and verbs come late in a sentence as a reliable revision cue, children's cognitive control engagement from that prior trial helps them revise. So the story is that, like adults, cognitive control simply promotes reliance on relevant over irrelevant information. But what is reliable to a kid just differs from what is reliable to an adult due to differences largely in language experience. So I'm going to leave you with that cliffhanger. And the final point I would say is that isolating states versus traits may inform theory development because trait individual differences, which really have been instrumental in our understanding of how non-linguistic cognitive systems contribute to parsing and interpretation, they only tell part of the story by virtue of the method, right? State-based approaches can reveal particularly more about how cognitive systems contribute to interpretation procedures, why and when they do as language input unfolds moment by moment. Thank you, folks.
Thank you so much. This was wonderful.
Thank you. Thank you. How'd I do on time?
You're
Jorge.
great. Perfect. So I'm not going to stop recording and open the floor for discussion.